Hello everyone. So in this session I'm gonna cover lecture 9, uh, which is the continuation of chapter 7 in your book. So we're gonna talk about uh, a topic that I mentioned in the previous lecture, which is the automatic repeat request. And then we're gonna talk about an example of a data link protocol. So let's dive into it. Okay, so last time I mentioned that we have techniques for flow control, right? And we mean by flow control is the mechanism that the receiver uses to slow down the flow of packets from the transmitter, right? To accommodate different speeds between the receiver and the transmitter. So the receiver can slow down the transmitter by withholding acknowledgement. And we saw two techniques of that. The one is the stop and wait protocol, where the transmitter sends a packet or a frame and then waits for the acknowledgement. And once the acknowledgement is received, another frame is sent and so on. This mechanism can be useful, but also has disadvantage of if the travel time, if the propagation time is long compared to the transmission of the frame transmission time, then a lot of bandwidth is waiting for the acknowledgement to come back. So to avoid this, we have the sliding window mechanism, where the idea is the transmitter can send up to a certain number of frames before waiting for the acknowledgement, right? If the acknowledgement comes back before the end of the number of frames, it can continue sending. If the frame or the acknowledgement is delayed, the transmitter stops until the acknowledgement comes back, right? And I said before that it's not always predicted, or cannot always be predicted, the sequence. Like, it's not always like we're sending 3 frames and waiting for acknowledgement, then another 3 and waiting for acknowledgement. No, sometimes things change. It depends on the condition of the network and the condition of the receiver. So we have to keep in mind always that there are a maximum of a W is the size of the window, so a maximum of W frames outstanding there without an acknowledgement at any given point in time. That's what you need to keep in mind. And while we have the discussion about this, I said some mechanisms are actually mixed with the control mechanism, error control mechanisms. For example, the acknowledgement may be not sent, not because the receiver doesn't want the transmitter to send any information, but because the receiver did not receive the frame correctly. So now it gets confused a little bit. Things start to get messy. Are we using the acknowledgement for error control, or we're using it to slow down the transmitter? So things get a little bit messy. In simple mechanism and simple um, uh, protocols, we can mix the two together, the error control and the flow control in one protocol. And we saw that we have a solution to that. We can say RR, ready to receive, right, to send an acknowledgement, and also asking for new frames to be sent. If I send RNR, received but not ready, this means that the receiver sends an acknowledgement, but say, okay, here is the acknowledgement, but please don't send me any more uh, frames. All right, so We will see later when we talk about, maybe in different courses, when we talk about TCP, for example, the flow control and the error control are separated and they're handled differently. Anyways, uh, in this lecture or in this section, we're going to talk mostly about error control, right? And what we will call the automatic repeat request. So the idea is, once error is detected in the frame, how can we control the error? By asking the transmitter to send the information back. That assuming, of course, that we don't have a mechanism to correct the errors. So we studied before error detection and error correction. So error detection is used most of the time when the price or the cost of retransmission is not a big deal, right? But sometimes the asking for retransmission is expensive. Imagine you are doing interstellar communication, right, between here and and another planet, another the moon or Mars, and it's not easy to ask for retransmission all that distance. So we rely more on the correction. Also, even on the planet Earth, we have situation where it's actually a lot easier to correct error than to ask for retransmission. So we will see in some protocols, actually, probably even in this course, that in some protocols we use error correction rather than retransmission. But for now, for this section, we're going to focus more on the simple mechanism of detecting an error, so asking for retransmission. We call that automatic repeat request. Right? So, so as the slide says, we have to we detect if we don't detect error, we will send a positive acknowledgement. So that's the ACK we saw before. Um, if there is no if we detect an error, we can send a negative acknowledgement, which means that we detected error, please resend. Or in some cases, the frame is lost altogether. So, of course, the receiver does not receive a frame, so it does not send a retransmission request because it never sent any, never received any frame. So in that case, we rely, or the transmitter rely on timeouts. So it sends a frame, it waits for a reasonable amount of time to receive acknowledgement. If the acknowledgement doesn't come back, it says, okay, there must be the frame must be lost. Either the frame is lost or the acknowledgement is lost. So I'm gonna retransmit the frame. So these are the basic mechanisms, and we will see how we put them together in different uh, uh, techniques. So there are actually three techniques. We saw examples of them before. So we talked about stop and wait. That's the simplest one. And we use that also for automatic repeat request, right? And then there is something called the go back in and something called selective reject or selective retransmission. Right? So we will see each one of them. So just a reminder, the stop and wait is simply as we saw before. Um, we have the two the pair of the communicating entities here, A and B. A frame is sent. We always use the slope to represent the time for propagation, right? Once the frame is sent, an acknowledgement is sent back. The transmitter waits until the acknowledgement is received. If it's received This means that the frame was sent correctly. So it sends another frame and the story continues. Right? And we saw earlier that to avoid some confusion, we will number the frames. So the frame 0 is acknowledged with ACK1, which means that the receiver is asking for the next frame, frame 1. And since we use only two numbers, either 0 or 1. Right? Okay, so the next mechanism is the go back in. This is or this mechanism is depends on the sliding window, right? So it is based on the sliding window. The idea of the sliding window alone is used for flow control. But if we do the go back in thing, um, we add the error control to it. So the idea, excuse me, the idea is um, can be explained by this picture here. So there are several examples. So we'll start by A sending frame 0. Now, since we have multiple frames that can be outstanding, that can go out without acknowledgement, we have to number them. So we will number them 0, 1, 2, 3, up to a certain number. So if we use 3 bits for sequence number, then we have from 0 to 7. All right. Numbers, the sequence number go from 0 to 7. So here the example says, okay, I'm sending frame 0, I'm sending frame 1. B receives frame 0 and 1 correctly, so it sends back RR2, which means I am ready to receive frame 2. Frame 2 has been already sent by that time. So you will see here continuous of sending um, as long as we are not exceeding the window size, the A will keep sending frames, right? Here, an example of why we are saying it's go back in. So frame 4 is sent and is lost. In the it never received by B. Frame 5 is sent also. Here, from B perspective, says, wait a minute, I am receiving frame 5, but I haven't received frame 4. So it's immediately sent something called reject 4, which is a negative acknowledgement, right? So it says reject 4. Now, because of the timing, reject 4 is received after frame 6 was sent. So from A's perspective, it has frame 4, 5, and 6 have been sent already. Once it receives reject 4, frame A says, okay, B hasn't received 4. That's why it is sending me reject 4. So I am sending frame 4 again, and not just frame 4, but all frames that was sent after 4. So I'm sending frame 4, frame 5, and frame 6 again. Right? And that's why we uh, call it go back in protocol, because we are going back 3 frames and sending all of them again. Not just the missing frame, but all of them, right? Since the last one that was rejected. All right, so I'm going to continue and then explain why we use this. It seems like a waste of bandwidth, right? If we are the 5 and 6 were received okay, so why we're sending all of them again? So I'm gonna explain this in a minute. But let's continue. So frame 4 is sent. RR5 is sent, so frame 4 is received correctly, frame 5 is sent, 6. Here we have a situation where the acknowledgement itself was lost. So 6 was received correctly, and B sending RR7, 7, the acknowledgement is lost. In the meantime, A continues sending frames, right? So A can send up to the window size of frames without waiting for acknowledgement. So frame 7 is sent, 0 is sent. At some point, A starts wondering, why haven't I received an acknowledgement yet? Right? Because the acknowledgement seems to be coming in certain patterns. So RR2, RR4, R reject 4. So they come in in a, in a predictable time frame. So if there is a timeout counter and the timeout counter runs out without receiving any acknowledgement, A starts wondering, maybe the acknowledgement is lost. So how about I'll ask B to send me a new acknowledgement? So it sends acknowledgement of special kind, its own acknowledgement. It says RR with a polling bit, so the P bit here equal 1. So this is a special type of acknowledgement that comes from A, not from B. It's a control frame that we will talk about later when we talk about the HDLC protocol. So it is sent from A to B. It's simply asking B, please send me an acknowledgement because I haven't heard from you in a while. So at this point, B has received 6, 7, and 0 correctly, so it sends RR1. It sends an acknowledgement of please send me 1. So A in that case will continue sending the remaining frame. Right. So you'll see here the sequence of events in the situation where a frame is lost or in a situation where the acknowledgement itself is lost. Right? All right, so I promised to explain why we go in a number of frames instead of just sending the missing frame. So this has something to do with the design of the, the receiver, right? If I want to keep the receiver simple, well, we need to have where those frames go anyway. When B receives the frame, where do they go? They go into memory. So imagine we have a memory at B, and the memory has slots for frames. So a frame 0 is received, so it's going to be put on a specific slot, and once it's received correctly, it's going to be sent to the upper layers. So this is the data link layer. It is the layer responsible for doing all of these error detection and windows and all of that. So F0 is received correctly. As soon as it's received correctly, it's sent to the upper layers. The receiver may receive up to a certain number of frames, process them, and then once they are received correctly, they can be sent to the upper layers, and then forget about them. That's the upper layers problem now, right? If a frame is not received correctly, let's say frame 0 is received correctly and it was put in the first slot here, then frame 1 is lost, frame 2 is received instead. Now, frame 2, if it was put here, this means that I am leaving memory unused until frame 1 comes, right? And this means that I have to keep at least 3 slots of memory or more just to handle missing frames, right? If I want to keep the design of the receiver simple, I have to use only one memory slot. And the rule is, if I receive a frame and the frame is in the right order, I will put it in this memory slot. I'll process it, make sure that it's received correctly, there is no error. And once I know that it's received correctly, I will send it to the upper layers and I will send an acknowledgement. Second frame comes, I will put it in this memory slot. I'll process it, do the error detection techniques on it. Once I know it is working fine, it is received correctly, I'll send it to the upper layers and I'll send acknowledgement. If I receive something out of order, let's say F3, I will completely and totally reject it, discard it, and I will send a reject. And I'll send reject 2, which means send me 2. Why? This way I will keep my memory small. I need only one memory slot for the frames. Right? That keeps my design simple. I don't need a lot of memory. I need just one memory slot for the frame. The drawback, of course, that any packets received out of order has to be rejected. And that's why when the when the transmitter receives the reject 2, it has to retransmit all of them. It goes back and retransmit F2, then F3, then whatever, all the others that was sent before. Because simply the receiver discarded them, so they have to be sent all over. Okay, so that's why we need to do the go back in. There are another topic here that I didn't mention, which is the window size. The window size here says it's W is equal 2 to the power n minus 1. So why is that? All right. Again, it has something to do with the rejection thing. So I said we can assign, let's say, only 2 bits to the sequence number of frames. So now we have frames 0, 1, 2, and 3, right? So we can call, we can have frame 0 is sent, and frame, let me draw it better here. So let's go back to our A and B. And let's say I'm sending, let's assume that W equal 2 to the power n, which is 2 to the power 2, which is 4, right? So this is the scenario where I have 2 bits to represent the sequence number of frames, or the frame number. So W, I'm going to put W as 4. So which means that A can send up to 4 frames without an acknowledgement. What's wrong with that? Okay, let's see. Now, A sends F0 and doesn't wait for the acknowledgement because it can send up to 4 without acknowledgement. So it sends F0, F1, F2, F3. And let's say F1 was received, but it has error. So simply after sending all of these frames, B sends an acknowledgement that says it doesn't matter whether it's reject or RR or whatever the acknowledgement type, it will say, let's say RR 0. From B's perspective, it's asking for retransmission of this. From A's perspective, it says, oh, all my frames have been acknowledged, and B is asking me to send a new frame 0. This is new, not the same as this one, the top one. So here there is a confusion happening. B meant to ask for F0 again, right? Because it was received an error. A thought B wants a new frame 0 because the sequence is over, right? So A sends 0, 1, 2, 3. So the next sequence number will be 0. It circulates. To eliminate this confusion, we are reducing the size of the window to make it 2n minus 1. Okay, how does this solve the problem? Well, now the window size in this case becomes 3, not 4, which means that A is free to send up to 3 frames without an acknowledgement, not 4. So it sends F0, it sends F1, F2, that's 3, right? And then it has to stop. If an error occurs, B will send RR0 asking for frame 0 again. Now A knows that there is no confusion. B is meant to ask for this one again, right? Because if all of these were received correctly, B would be sending RR3, not RR0. So in this case, because of the go back in, A will start sending frame 0 again, and then frame 1, and then frame 2. Here, B will send RR3, so A will send frame 3, and then frame 1, frame 0, and then frame 1. And notice that I always have no more than 3 frames outstanding without an acknowledgement, right? So you always practice counting how many frames I have out there without an acknowledgement. And they shouldn't be exceeding W, the window size. It can be less, but not more than the W. Okay? Obviously, this technique has a problem and has an advantage. The advantage is I'm keeping the design of the receiver simple. I need only one memory slot for a packet. But the disadvantage is if there is any error in the frames, all the frames that were sent after that frame, they have to be retransmitted, which means a waste of bandwidth because we are retransmitting frames. Okay, so let's use another technique then and see if it helps improve. So the new technique is called selective reject or selective retransmission. So here the transmitter when it receives not the retransmitter, um, the receiver when it receives um, let me let me say it again. So the receiver retransmits only the rejected frames, right? Not all the frames after that, just the rejected frames. Right? So here is an example. So it's similar. So if you compare the two, they're the same, almost the same graph. Um, so the differences starts when frame 4 is sent here, right, and it's lost. Frame 5 is sent, so here B thinks, oh, wait a minute, I haven't received frame 4. So it sends a selective reject 4, which means that please send me 4. Here, A does not send or resend all the frames again. No, it sends only frame 4, and then it will continue with the sequence frame 7, frame 0 as usual, right? So it's better because now if you compare this one, I sent 4, 5, 6, and then I sent them 4, 5, 6 again. So I wasted bandwidth resending frames. Here, I didn't waste any bandwidth. I selected, I retransmitted 4 and then continued with my normal sequence 7, 0, 1, 2, and so on. So actually, as a matter of fact, when you compare the two, I sent 2 more frames by the end. So here frame 1 and frame 2, here it's frame 3 and frame 4. So I sent 2 more frames in the same at the same time, which better efficiency, right? The issue here is we need more complicated design. So as I said before, if I want to send or receive frames in out of order, it means that the receiver has to make sure that it has enough memory to receive frames out of order. So let's say I received frame 0, so I'm gonna process it, right? Make sure that it's everything is correct, and then send it to the upper layers. Okay, so let's say I received frame 2, which means that I am missing frame 1. So here, where is frame? The receiver has to say, okay, I'm going to leave a space, a memory, to frame 1, and I am going to process frame 2, make sure that it's received without an error. But I cannot send it to the upper layers yet. Upper layers expecting the frames to be in order. So I cannot send it to the upper layers yet. It has to be saved. So let's say frame 3 is received correctly, so I'm gonna put it here. Frame 4 received correctly, so I'm gonna put it here. And I have to put all the frames one by one in memory and hold the memory up until finally frame 1 comes. So I'll put it here, make sure that it is received correctly, and then only then I can send all the frames to the upper layers, because they are expecting things in order, right? So this means that the receiver has to have enough memory at least for the size of the window to make sure that, because I may have a window of 7 and the first frame is lost, all 6 frames are received. So the 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 receiver has to keep all 6 frames in memory until the one that's missing, which happened to be the first one, until it's received correctly, then I'll send all of them to the upper layers. So I need more memory, right? There's also another issue with the selective reject technique is that the window size have to be smaller. Compare window size here. If I have n is the number of bits that are used for the sequence. For the go back in, we saw that w has to be 2 to the power n minus 1. For the selective reject, they have to be 2 to the power n minus 1. N minus 1 is the power, right? So this is not a typo. So it has to be, so if n is 2, then uh, the window size is not 3. The window size is actually just 2. If I have 3 bits, so n is 3, then in the previous case, the window size is 10 to the power 3, which is 8, minus 1, which is 7. So the window has to be 7. Here, it's 2 to the power 2, which means 4. So the window size has to be almost half of that of the go back in. So why is that? So to explain the situation here, why we need half of the window, well, let's assume that we have A and B again. And let's assume that we have a window size of, or the sequence number is 2. So the window size, the original window size, like before, is 2 to the power 2 minus 1, which means that we have 3. Right? So here, A, in the slides, we are assuming window size of 7. Now I'm just using it smaller. So A sends F0, then sends F1, then sends F2, right? B sends an acknowledgement, says, oh, I am ready for 3 now. But let's, luck has it, B or the acknowledgement is lost, right? So A waits for certain timeout and then said, I didn't receive any acknowledgement, so maybe my frames were lost. I'm gonna send them again. So it starts sending frame 1, frame 0, frame 1, and so on. B doesn't know that its acknowledgement were lost, so it assumes that these are new frames, not a duplicate or or the same frames again. But they are out of order because it is expecting 4. It is expecting frame 3. So it sends a selective reject REJ 3, which means that the receiver receives F0, F1, doesn't reject them because it thinks that they are new. So it receives them, but it sends selective reject 3, which means that, oh, I received these frames, but please send me 3. So now there is a confusion, and also there is a problem that B receives duplicate frames. We don't like duplicate frames, and we don't like frames with errors, right? Duplicate frames will be sent to the upper layers, and they will be mistaken by new frames, which is a problem. So, and that's why if we reduce the size of the window to 2n minus 1, so that problem disappears, and we won't have this issue. So if our n is 2, then we end up with 2 to the power 1 and only 2. So the disadvantage here is for the selective reject technique is our window is smaller, which means that we're not be able to send as many frames without acknowledgement as we used to before. So we have an advantage and disadvantage in this case. Okay, we talked about the efficiency of the two of the stop and wait before. I explained it to you. So I'm going to explain it now, and I'm going to talk also about the efficiency of the sliding window, right? So this is a repeat of what I mentioned before. To explain, let's say this is the stop and wait protocol or mechanism. Remember, a frame is sent, and to keep things in scale, we have to watch for the number of the boxes here in my sheet, right? So a frame is sent. We always need some some time, which is the propagation time for the first bit to be sent, and then we have the frame size. So the frame itself takes time to be sent. Never forget that. Sometimes in our diagrams, we don't represent the frame as thick line like this. We represent it as one line. That's just so that we can simplify the diagram a little bit. But to consider efficiency, we have to look into the full diagram. And then we are sending acknowledgement. The acknowledgement also, if you look at it, it takes TP to be received. Acknowledgement has a size as well, but we will assume that the size is negligible, so we will represent it only with a single line, okay? Just for the simplification. But actually, for the full analysis, you have to consider the time for the acknowledgement to be transmitted. So we'll call that TA, for example, A for acknowledgement, and this is the time to send an acknowledgement. And also we need to consider the time for the receiver to process the frame. So it may need what processing needed. It needs to check the error. For errors, it need to process it and send it to the upper layers. It needs to do other things. So also there is some time. So the rather than sending the acknowledgement immediately like this, it may be sent after a while, right? But we'll just make things simple. So here, if you look at this, this is what we'll call T total, which is the total time from the beginning of the transmission until I am able to send another frame. This time consists of, just to make it clear here, consists of TP, two of them, 1 and 2, 2TP plus TF. That's the total time. Within this total time, the time that was used effectively was used actually to send data is TF. For the rest is wasting time, just waiting, doing nothing, right? Waiting for acknowledgement. So the utilization of this channel is TF, the useful time, over the total time, which is 2TP plus TF. And that, if I divide both sides by TF, I end up with 1 over 2TP over TF plus F. This quantity, we'll call it A, and this is a normalized time, right? So uh, rather than dealing with a lot of TPs and a lot of TFs, we could assume that, let's say, the TP is half of the TF, so A will be a ratio, right? So it will be 8.5, or the TP is 1.5 of the TF, which means A is 1.45. So this allows us to normalize the values so I can deal with them instead of dealing with any number of. So a ratio is easier to deal with. Okay, so how about the case where I have a sliding window? What is the efficiency here? Okay, so I'm going to repeat. Let me clean it up a little bit. So for this case, the W is 1 over 2A plus 1. And for the window size, I'm going to have my lines again. Okay. Let me try to make the lines better. All right, not much better, but anyways, so let's have an assumption here that the frame size is actually less than the propagation time. The transmission time of the frame is less than the propagation time. So I'm going to have this slope here a little bit uh, steep. So this is my T propagation, and this is my T frame, TF. And as we mentioned before, in the sliding window or go back in protocol, we are allowed to send W number of packets or frames before waiting for the acknowledgement. So the acknowledgement, let's assume that the acknowledgement is sent immediately, right? Sent immediately here. As soon as the receiver receives the first packet, it sends acknowledgement immediately. But of course, it will take some time to arrive, so A will continue sending frames up to the window size. Let's assume the window size is 4. Just for now, we have 4 packets. So the window size is 4, and we assume that the propagation time is 3 units, and the TF transmission of a single frame is 1 unit. So what is the total time? We'll do the same thing. We will divide the useful time by the total time. So the total time here, this is T propagation, this is TF, and this is T propagation, right? And this is our total time. This is the total time to send a window size of 4 frames and waiting for the acknowledgement before start sending more frames. So the utilization will be how much time I spent sending frames is W multiplied by TF. How much time I waited overall is 2TP plus TF. Right? If I divide things again, I will see that W equal 2A plus 1. Oh, sorry, U equal W over 2A plus 1. Right? This works if WTF less than 2TP plus TF. Right? So this formula works if the total time to send 4 frames is less than the total time to send the frames and then wait for the acknowledgement, right? And if I divide this by TF, I see W equal 2A plus, less than 2A plus 1. So that works in this condition. Okay, what if, now let's consider another scenario. A scenario where the frame, so look at the scenario here before, and then we will consider another scenario where the frame size is actually more than, or TF is more or is greater than TA. So here we have, this is our TF and this is our TP, and as I said before, we continue sending frames so that's frame 0, frame 1, frame 2, frame 3, up to 4, right? But the acknowledgement here is sent, let me choose a different color so I can send the acknowledgement comes back here. So when the acknowledgement comes back for, let's say, RR1, the transmitter can send more frames and the acknowledgement comes back. You see the acknowledgement comes back and on time, so the transmitter never have any time wasted waiting for acknowledgement. Unlike before, here TP was a lot more than the TF. So the transmitter had to be forced to wait for an acknowledgement. Here, the acknowledgement comes fast because the TF is actually greater than the TP. So the acknowledgement comes fast compared to the TF. So W here is, or the utilization is 1, which means that I'm utilizing the channel 100%. There is no waste, right? And the condition here is W is actually less than or equal to A plus 1. So, and that's what was mentioned in the slides. If you can see here, the utilization, we have two cases. The first case is when W is less than 2A plus 1, and the other utilization when they are when W is greater than or equal to A plus 1. So in other words, if we have a T propagation much larger than the TF, we need to have a large window size. We have to make the window size, the larger the window size, the better utilization. Right? The larger this number here at the top, the better the utilization. If this number is small, and in the worst case scenario is just 1, right, the utilization will be small. So we need to keep W as big as possible. If it's the other way around, if the TF is greater than TP, so the time to transmit a frame is actually much larger than the time for the propagation, then we always we always have we can have a full utilization by making W equal TA plus 1. And of course, make sure that the W is integer, right? So if A is 0.9, then 2.9, that's 1.8 plus 1, 2.8. So the window has to be not 2.8, the window has to be an integer. So the window has to be 3, for example. So make sure that the window size is actually integer because we have integer number of frames to send. Okay, so our next topic is the protocol, a protocol called High Level Data Link Control Protocol, or HDLC protocol. This protocol is an old protocol, but we are still studying it. Why is that? You see, in this course, we have a lot of legacy protocols, old protocols that we keep still studying them, even though they are not used anymore. The reason for that is some of this knowledge, some of the techniques that we learned from these protocols are still valid today, and we see them in modern and existing protocols. So HDLC is good for study because it has all the techniques that we studied, the stop and wait, the CRC, the error detection, the selective reject, all of these can be used in HDLC. So before I continue, HDLC was used for synchronous transmission, right, as opposed to asynchronous. I think we talked about asynchronous in another lecture, but the synchronous transmission means that we are sending a frame as a sequence of bits, and um, we are marking the frame, right? So we are delimiting the frame. We're having a start and end, and everything in between the start and end is part of the frame. Right? And the asynchronous techniques that we talked about earlier, I think, is that we are sending 1 byte at a time, and the byte itself has the synchronization. So we have a start bit, an end bit, and parity bit, and all of that. So we are sending 1 byte at a time. Here we're sending 1 frame at a time. In order to explain, before we talk about the frame structure, I want to explain what was the protocol, or why the protocol was created in the first place. So a little bit of history. The protocol was created back when the idea of communication, even before network happened, is we have a mainframe, those giant computers that you see them probably now in historical movies, and the mainframes used to connect to what's the so-called peripherals. So the peripherals could be a giant terminal or um, tape records or a printer. So those are peripherals, and the peripherals, the mainframe sends data or receives data from these. The frame needs to communicate to these frames, so they need to be addressed. So we can address them by giving them 0, 1, 2. So that's the address. When they are to communicate back, they don't need, they usually, the peripherals don't talk to each other directly. They talk to the mainframe only. So when they talk back, they talk only to the mainframe. So the mainframe, when it wants to talk to the terminal or any other peripheral, they will need to send the address as a destination address so that the printer knows that the packet's coming not for it but for the terminal or for the tape. And when the peripheral sends data to the mainframe needs to know where the data is coming from. So one of the implications of that is that we don't have two addresses, source and destination. We only have one address field in the packet, in the frame. That address field refers to the destination if the packet is coming from the mainframe. If it's going to the mainframe, that address field represents the source, right? So we don't have two addresses as we used to before. Also, because in those days, the mainframe is the one that controls the conversation. So the mode of communication, we call it master-slave. So none of these peripherals can initiate traffic unless the mainframe asks them to do so, right? Later on, the protocol was modified so it allows for bidirectional or balanced communication where either side can talk to the other without having permission, right? So we will see this later when we talk about the details. Okay, so now that I gave you a little bit of history, we'll see that the frame itself is divided into blocks of 8 bits. The first and the last bytes representing flag. So the flag is the the demarcation of the frame, and they always have the same content 0610, right? So every time either device, the receiver or the transmitter has to put the flag, the receiver, when it sees 0610s, means that this is the start of the frame and start interpreting the content after that accordingly. So the next 8-bit is the address, and we'll see here that it can be extended to 16. So the protocol means that it's capable of handling up to 255, 256 different peripherals, right? And they can be expanded to 16, so that's 2 to the power of 16. We have control field, we have information field where the actual data goes, and then we have the FCS, frame checksum, and it uses the 16-bit CRC, CCITT, right, or the CRC32, so it can be either 16-bit or 32-bit, and ends with a flag, also 0610. Right? So The first thing we have an issue with is the flag. All right. So when here we assume that if we have 0610 here, it means that we cannot have the same pattern of 0610 everywhere else. If we put an address, one of the devices has the address 0610, we may confuse the receiver on thinking that, oh, there is a flag and then there is another flag, so the frame has a zero length, it's ended. If I have the information here that contain any byte within the information that contains 0610, also we confuse the receiver, because the receiver, as soon as it sees 0610, thinks that this is the end of the frame. So we need to make sure that within these two boundaries, within these two flags, there is nowhere in the bits we see 0610, which means that we have somehow to modify the content inside the frame to eliminate any chance of having 0610 pattern in it. So to do that, we have to rely on something called bit stuffing. So the bit stuffing looks at the original pattern, like the one at the top here, and see, okay, so ones, 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 one, 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 okay, that's all fine. But here we have 0610. That's a problem, because if the receiver sees this, it will think that it is the end of the frame and stop sending, it stop receiving. So the rule of the bit stuffing is we have to make sure that we don't have more than 5 ones, consecutive ones. Every time I see 5 ones, I have to insert a 0 to break the sequence. So here I'll count 1, 2, 3, 4, 5, and insert 0, and then count again 1, 2, 3, 4, 5, and I insert 0, and then count 1. So here's already 0, so I don't do anything. And here I have 6 zeros, so I have to insert 0 to break the sequence. So make sure that I don't have any 6 zeros. Okay, so the receiver will do the same thing to retrieve the original data. It will start looking at the sequence and say, okay, I have 5 ones, so there must be a 0 after that. If there is a 0, I will remove it and continue. If there is no 0, then there's two possibilities. If there is a 1 and 0, this means that I have 6 ones and 0, which means the flag. And I will assume that this is the end of the frame. If I see 6 ones, but then there is no 0, there is another one after that, then I abort. I say, well, this possible error. I cannot handle that. So you'll see here there is all of these scenarios, right, written here. That bit stuffing is not foolproof. Right? I may still have issues. Let me explain what are the issues. Let's assume I have a frame that has 0610 and then sequence of bits here, and then 0610. So that's proper frame. It has a starting flag and an end flag and a sequence of bits in between. And the sequence of bits, because of bit stuffing, They don't include any 610, so they are good. But let's assume within this we have 0, 3 ones, 0, 1, 1, 0, right? Something like this. And then the remaining bits. Let's say due to error, this bit is flipped from 0 became 1. So now the receiver sees a flag, a sequence of bits, and then another flag. So it thinks that this is frame and this is another frame. It thinks that it received actually 2 frames, especially that actually HDLC allows merging 2 flags together, so it doesn't have to be flag, content, flag, content. So it thinks that it's actually receiving 2 separate frames, and of course one of them will not make any sense at all, so it will be a problem. The opposite scenario could happen. The opposite scenario could see 2 frames sent back to back, so these are 2 legitimate frames sent back to back. That's frame 0 and that's frame 1. Because of error, this flag in the middle is flipped, or one of the ones is, flipped. So actually, this will make the receiver think that these are actually one big frame. Remember the frame size, the information could change, the size of the information could be big or small, so it will think that this is an actual big frame, right? So that's one of the drawbacks of having this flag thing and the bit stuffing. Anyways, so aside from that, let's take a look at the control field. So we talked about the flag. Now let's talk about the control. And I mentioned the address. Address is 8-bit or 16, and it can be used to address the peripherals. The control, we have actually 3 different formats of the control field. And by default, the control field is 8-bit, but it can be expanded to 16, right? So let's take a look at the first scenario. If the first bit in the control field is 0, we will call this information frame. And the information frame is a regular frame that carries data, right? So we will see here that we have 3 bits of the sequence number. These are used to number the frames. Remember when we talked about go back in protocol, we need to number the frame 0, frame 1, frame 2. So this is where the frame number goes. We also talked in the previous lecture about piggybacking the acknowledgement with the normal frame. So this is the acknowledgement field, also 3 bits, and it's used to piggyback the acknowledgement on top of the regular frame. We also talked about this polling or poll bit. I'm going to explain it further later, but we saw it before when one of the transmitter sends a poll to the receiver asking it to send back an acknowledgement. That's this is the bit that we were talking about. But it also has another another reason that I will explain. Okay, so if the frame of the control field starts with 1, 0, then we will consider this a supervisory frame. The supervisory frame is the acknowledgement frames that we talked about before. So they are used for acknowledgement. So all of those RR and RNR and reject and selective rejects are are supervisory frames. And we see here that we have remember the acknowledgement, they have a number, so that's the NR. And also there are two bits here, 00011011. So we can represent RR, RNR, selective reject, and reject. Each one of them can be one of these S here. So these the supervisory function bits. All right. The final control fee or the control type is the unnumbered. These start with 1, 1, and we have 1, 2, 3, 4, 5 bits for different functions. All right, so we will see one of these functions in a minute. The control, the HDLC can be expanded. So here in the information frame, we have 3 bits for frame numbers and 3 bits for the acknowledgement, which means that if I use go back in protocol, I have to use a window size of 2 to the power 3 minus 1, so the window size of 7, right? Window size of 7 may not be big enough for some applications. If I double the size and go from 8-bit control field to 16-bit, then I have now 7 bits for the frame and 7 bits for the acknowledgement. 7 means that I have 2 to the power of 7 minus 1, so I have up to 127. The size of the window is huge this time, right? So I have a lot of frames to send. So what is that P field? Remember when I said the HDLC main or original use was to communicate between mainframes and peripheral devices. So, and that's where we need to use the P bit. So if the mainframe wants to talk to one of these peripherals, it sends the frame with the P equal 1. And this means that I am asking for information. This is polling. I'm asking for information. When the peripherals send back a frame to the mainframe or any controller device, the bit changes meaning and becomes F. So the mainframe doesn't know how many frames the printer will send or the tape will send. So it may be 1 frame, it may be 10. So it has to know if the device has finished sending all the frames or not. So the device will send the F bit as 0 at first, and then continue sending 0, 0, 0 until it's done, until it has no more frames to send. So when it's done, it sends F as 1, means that it's finished. Right? So, and that's the meaning of, so the P bit is sent, if it's 1, then means that the mainframe or the master wants information, wants a response. And when the response comes back, the F is used to say I am done, or I still have more frames to send. And we will see it here in one of the, we will see it here. Okay, so I also mentioned that later on HDLC was used also to communicate between two devices, A and B, in a balanced, so nobody is the master and the other one is slave. Both are working at the same level. And here we can use HDLC to do a connection-oriented, or use it as a connection-oriented protocol. So a connection-oriented protocol means that we have to make sure that the other side is ready to receive before sending any information, right? While in connectionless, we are sending information without waiting for without actually checking if the receiver is uh, is waiting for us, or even ready to receive our frames. So we will talk about connection oriented versus connectionless later, but these are the main issues or the main differentiators for now. So in order for one side to start talking to the other, it has to send a connection request. So here A keeps sending this. So which packets which control fields we use? We use the unnumbered. For this type of communication, we use the unnumbered control fields. So one of these fields, remember we have M here, so each sequence of bits represent a function. So one of these functions is SABME, which is start async balanced extended mode, right? So A wants to start this mode, so it starts sending these control fields, a frame that has the control field SABME, and it keeps sending until it receives unnumbered acknowledgement. Again, the unnumbered acknowledgement is using one of these unnumbered. It doesn't use the supervisory acknowledgement. It uses one of these. So it sends unnumbered. Why it sends unnumbered acknowledgement? Because these don't have a sequence numbers. So to acknowledge them, we cannot use a sequence number. We cannot use an acknowledgement like before, RR0 or RR1. So we have to use something called unnumbered acknowledgement. So that will start the connection. And then in between, we'll start sending information as before, information and acknowledgement, information and acknowledgement. So as before. And then at the end, the side that started the connection says disconnect. So it sends another control field that says disconnect. And B says, okay, I acknowledge that. So both sides agree on disconnecting. And this is an example of connection-oriented communication. Okay, and as I mentioned before, HDLC has all the examples that we talked about. So I'm going to talk about some of these and leave the others. So we talked about sending information and receiving acknowledgement. So here, this I represents an information field that's coming from A. It has a sequence number 0, and it has an acknowledgement piggybacked, also 0. B sends information back, so this is both sides sending information to each other. So it has the information field has a sequence number 0 and has an acknowledgement 1. This means that I am ready to receive frame 1 from you. So you'll see here, this is an exchange of frames between the two sides, each one sending information and acknowledging the other, right? At the end, frame or the A, device A, doesn't have any information to send to B, so it sends just the regular acknowledgement, RR4. Here an example of sending RNR, receive not ready. So this is an example of B is sending information to A, but A is busy, right? It doesn't want to send information. So it's sending an acknowledgement. It says, I received 3 and I am ready to receive, and the next one is expected at 4, but don't send me anything. So I am not ready to receive anything. B, after a while, sends a polling, say, well, I acknowledged your frames here, but are you still, do you want me to send something? So this is an example of here it's sending back, no, I'm still not ready to receive anything. And F is the response to the P, so I'm done talking to you right now. So this exchange of information happening, this is an example of eventually A says, I am ready to receive, so B starts sending packets again. Here is an example where HDLC is used to implement selective reject, or implement actually go back in. So it's A sends frame 3, sends frame 4, sends frame 5. Frame 4 is not received correctly, so B sends reject 4. So A sends 4, 5, and 6. So that's an example of go back in. And this is an example of also same thing, go back in, but there is a timeout. So that brings us to the end of this lecture. Thank you very much, and I will see you in the next one.